Alright, y'all, what's up? What's up? You've caught me on Wacky Wednesday, but I've got some calculus to teach you. Let me share my crap. Alright, there it is. And then I'm teaching you this section. It's a long name, but it's called partial fraction decomposition. So the idea behind partial fractions is this. It is that let me show you the idea going backwards, which is the more normal direction that you already know. It says basically this little paragraph that I'm pointing at right here with the mouse just says that you already know when you have two fractions and you're trying to add them or subtract them, then you need a common denominator. And so if I were to get these two fractions together, I would get the common denominator, multiply this one by x plus 4 over x plus 4. I would multiply this other one by x minus 1 over x minus 1. Foil everything out, combine like terms, and I'd end up here. But what partial fractions decomposition says is that it works backwards as well. So basically, what I'm saying is, if you were to start at the combined fraction, and you were to factor the denominator into the x plus 4, x minus 1 that it factors in, then partial fraction decomposition says you can break down this big fraction that I circled in black into these two fractions where each factor gets its own fraction. I believe that's all I want to say about it before an example, but let me just scroll through this and make sure I don't want to say anything else. Making integrals. It's saying that if you were in college, you would need to learn some more complicated cases than you need to learn here in AP Calculus. But if you're interested, I can probably show you videos of how to do the more complicated cases. But like I said, on the AP Calculus test, you only need to know, and on my test, you only need to know one specific type of partial fraction decomposition. Here's the stuff right here that I'm pointing at. That's stuff you don't have to know. The one thing that you do have to know is what I'll show you in the example. And this little box just says, maybe at a higher level than just high school, this is kind of a complicated way to say that if the denominator of a fraction factors, then you can break it up so that each factor gets its own fraction. Again, I'll show you what this means in an example. So here's an example. Let me scroll from the... I'll just scroll. Oh. Scroll. All right, there's the first example. Okay. So here is an integral that I want to take. You see the integral of a fraction, and you're thinking, can I take that integral straight up? Like, do I know the antiderivative of that right away? And the answer is no. Does u substitution work would be the next thing I think of when I see fractions? And the answer is no, because if I make u be x squared, don't write this because this is wrong, x squared minus 7x plus 12, and I take du, I get this extra 2x minus 7 that is nowhere to be found on the integral. So the derivative of the u isn't in the integral. That means that the u substitution doesn't work. Okay, so that doesn't work. Does completing the square work? No, for reasons that I can show you later, but basically you don't get the... If you're going to complete the square, you want something that looks like that, and that would not be what this looks like. That would look like x minus something squared doing that in my head correctly. But the short version is, none of the things that you know work. Okay, so what do you do instead? You do this partial fraction decomposition that I was talking about. So, a quick way to check if partial fractions is going to work is, does the bottom of your fraction factor? If it does, then it's going to work. If it doesn't, then it's not going to work. Even if U substitution would work on this, if the bottom factors, then partial fractions would also work. So that's a quick check, is like, does the bottom factor? Yes. Oh, okay, then I could do partial fraction decomposition. So here's how it goes. Factor the bottom of that fraction, and it looks like adds to 12, adds to 4 and 3, minus 4 minus 3. X minus 4, x minus 3, dx. Okay. Then, you know, because of what I told you earlier, people smarter than us figured out that you can break down this fraction into two fractions because of the two factors here that look like something that I don't know yet over x minus 4 plus something I don't know yet over x minus 3. Okay, and like I said, once I combine these equations, once I get a common denominator and combine them, I should get back to the original numerator. So what do I mean? I mean that if, let me do some side work over here. If I add these, I should get back to this. So what I mean is if I multiply this one by x minus 3 on top and bottom, and this one by x minus 4 on top and bottom, then the result will just give me a 1 at the end, the 1 from the original numerator. So what's that mean? That means a times x minus 3 plus b times x minus 4 needs to be equal to the one that I had to start with. Okay, very cool, that's nice. So then how do I solve this? Because there's a bunch of different variables, a, b, and x. But the thing is that x isn't really a variable, because this needs to work for any x. I can explain that more in person, but just take my word for it, this needs to work for any x that you plug in. So x isn't really a variable, you're just trying to figure out what is a and what is b. And so since this equation that I'm circling here with my cursor needs to work for any x, if you choose strategic x's, then it's really, really, really easy to solve for a and b. So watch this. A good strategic x might be if x is 3, and I plug that in, then look what happens. A times 3 minus 3 plus b times 3 minus 4 needs to equal 1. Well, 3 minus 3 is 0, so I don't care about this. And then 3 minus 4 is negative 1b needs to equal 1, meaning that b must be negative 1. Okay, so I got my b, and then I choose another strategic x. Let's scroll down a bit. I choose another strategic x, like for example, if x is 4, then that makes the b part 0. So that would look like a times 4 minus 3 plus, I mean, you can see that this is going to be 0, so I won't write this every time. But for the first example, we will. 4 minus 4 is 0, 0 times b is 0, and then a times 4 minus 3 is 1. So 1a equals 1, meaning that a is 1. Cool! Okay, so now that you know your a and b, go back to your integral, plug in a and b, and take the integral of those, the antiderivative. So back to my problem that I really care about, that goes like this. Integral of a, which was 1, over x minus 4, plus b over x minus 4. B was negative 1, so let me write it like this. Negative 1 x minus 3 dx And then this is just a really quick natural log type of integral. You got 1 over x minus 4 dx. Let me split up the integral so that it's easier to deal with. Okay, and then technically there's a u substitution that needs to happen here, but you can kind of skip that if you're careful. So for the first example, let me do the u substitution, but most of the time I'm going to skip it. Watch this. U substitution would be, you make u be if you make u be x minus 4, and then du equals dx, which is exactly what you need. So this first integral turns into 1 over u du minus, I'll deal with that second integral in a second, and then this turns into natural log of absolute value of u, and u was x minus 4. So it's just going to turn into the natural log of the bottom of this. Just be careful that you're careful about that, because had the derivative of the bottom been anything other than 1, see how the derivative of x minus 4 is 1 dx, had it been 2 or negative 1 or anything like that, then this u substitution would have been important, and you can't skip it. So just be careful that the derivative of the bottom really is 1 if you're going to skip the u substitution. Okay, but back to here, this would turn into, if I make u be x minus 3, it turn into 1 over, because du is equal to dx. That blue integral just turns into 1 over u du. That's minus 10 natural log of u, which is natural log of x minus 3. And now that I'm noticing, maybe I should have used a different letter here, so let me call this v, 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 v. All right, there you go. And then put a plus c at the end, and you smile because there's your antiderivative. If you don't believe me, take the derivative of this red minus blue. You should end up with these two fractions, which add up to be this fraction right here. All right, hopefully that makes some sense. Next example is similar. Okay. So again, integral of a fraction, see if the bottom factors. If it does, then partial fractions is going to work. Well, yes, it will. If it factors into unique factors, had it factored like this, then that's a more fancy type of, like if you get two factors of the same type, that's a more fancy type of partial fractions, which we don't learn in AP Calculus BC, but you don't see this that often. Let me just say now, I'm hesitating. If it does factor like this black one, then you might need to try some U substitution or something. Because you don't learn this type of partial fractions in BC. Okay, so let me check if the bottom of this factors. It should, because we're in that section of the notes. So this would turn into 5x minus 3 divided by x minus 3 and x plus 1. Cool. All right. So now it did factor. So I know that that integral has to be equal to, I can split the fractions into something over x minus 3, which I don't know yet, plus something over x plus 1, which I don't know yet. All right, cool. So now I just need to find out what a and b are. So let me do my side work over here. A times x plus 1 plus b times x minus 3. I'm kind of cross-multiplying, if you will. Again, it's like if I were to combine these and get a common denominator, then the result needs to be equal to my original numerator. What was my original numerator? Oh, 5x minus 3 right here. Okay, and then if you're scared, like, oh, this one's going to be harder to solve for than the other ones, no, remember the x isn't actually really a variable. X needs to work every time. So choose some strategic x's, and that'll solve for your a and b very easily. So hopefully you can tell a good x to pick would be -1, because that makes the a part 0. Let me not even write it. A would go to 0, and I would get b times -1 minus 3 is equal to 5 times -1. Again, x would be -1 minus 3. This gives me -4b equals -8, meaning that b must be 2. Okay, cool. Now I got b, and then a, I can choose another strategic x, like x equals 3 would make the b part 0. That would just give me a times 3 plus 1 is equal to 5 times 3 minus 3. That gives me 4a equals 15 minus 3, which is 12, and then a equals 3. Nice. So side work is done. Now I got a, now I got b. I put those back into my integral. A being 3 over x minus 3. And then let me split the integral right now, right away. All right, and then sometimes I like to take the constants on top out, just so that it's very clear what the antiderivative is going to be. So you could skip this step because you're going to get the same answer either way. But just to demonstrate, those integrals are equivalent to the ones that I'm writing with the constants up top pulled out of the integral. And then, like I said, I'm going to skip the u substitution because the derivative of the bottom here would be 1. Derivative of the bottom here would be 1. The u substitution isn't going to affect anything. It's not going to, I don't need to account for an extra negative or whatever, have the bottom had a negative derivative or something. So I'm skipping the u substitution, and I'm getting 3 natural log of x minus 3 plus 2 natural log of x plus 1. Plus c. Cool! All right, there you go. Now, in my head, I'm thinking maybe they want an example where the u substitution cannot be skipped. So let me give you one of those. Let me add a page in here. Add a page. Add a page. All right, there you go. So when would u substitution not be allowed to be skipped? Like this. If you did all your partial fractions, blah, 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 and you got to this point, like a fraction like that, then the u substitution cannot be skipped because of this extra 2 here that you have to account for. U equals 2x plus 1 tells me that du would be 2 dx. And since I only see a 1 up here in the top of the fraction, I need to do 1/2 du equals dx, meaning that this integral turns into 1/2 in front, 1 over u du. So I get 1/2 natural log of 2x plus 1 plus c, which is not what you would have gotten had you just skipped the u substitution and jump straight to the end. So there's an example where u substitution cannot be skipped. Again, in the previous problem, it was all good because the derivative of the bottom was 1. All right, last one. Okay, so this one has a x cubed on top and an x squared on the bottom. The thing that I forgot to mention at the beginning of the class, or of the video. Here's me skipping to the very top. Is that the degree of g, so the degree of the bottom has to be bigger than the degree of the top. So the fraction needs to not reduce. So what I'm saying is, in that one that I'm looking at, the reason I was hesitating is because it's not ready for partial fractions yet. You have to first do some long division, make the fraction irreducible, like by doing the long division, and then you can do the partial fractions. So long division, if you forgot, here's a quick review. I'm trying to divide x cubed minus x plus 2 by x squared plus x minus 2. Bottom, the top. So top divided by the bottom. Top divided by the bottom. And then it goes like this. You just look at the leading terms. X squared times what would give me this x cubed? So it would be x, of course. Okay? And then what's the result of multiplying this by x and subtract that off? So x times x squared would be x cubed. X times x is x squared plus x squared. X times x, no, sorry, I already did that. X times 2 would be minus 2x, and that's it. And now subtract that off. That would be x cubed minus x cubed is 0. That's how you know you did it, right? Nothing x squared, maybe I should have written that here, but 0x squared minus positive x squared would be negative x squared. Negative x minus negative 2x would be plus 2x, so positive x. And then 2 minus nothing, 0, would be 2. All right, okay. Now you check again, check the leading terms, and you do x squared times what would give me negative x squared. So of course that would be negative 1. Multiply this polynomial by negative 1 and subtract that off. So that would be negative x squared minus x plus 2. Subtract that, and you're going to get negative x minus negative x is 0. Positive x minus negative x is 2x. 2 minus 2 is 0. So I get 0 plus 2x, or just 2x, I could say. All right. So then 2x is how this simplifies. Or sorry. The fraction divides to make x minus 1 with a remainder of 2x, because I can't multiply x squared by anything to make 2x. This is my remainder here in blue that I'm circling. And so I gotta rewrite this integral. Let me box that off because that was side work. So this integral is going to turn into, well, the fraction reduces down to x minus 1 plus a remainder of 2x over x squared plus whatever. So 2x over x squared plus x minus 2. Cool. And then that is an integral that I can handle, because antiderivative of that polynomial I can do, antiderivative of this I can do with partial fractions, and then that's the whole integral. So let's do it. Antiderivative of this would be x squared over 2 minus x plus antiderivative of this fraction. What's the antiderivative of the fraction? Well, I need to do partial fraction decomposition. So how does this factor? This turns into x squared over 2 minus x plus 2x over, how does this factor? X plus 2x minus 1. Okay, so then partial fraction decomposition says That can turn into, again, x squared over 2 minus x that I had from this, plus integral of something over x plus 2, plus something over x minus 1 dx. All right, what is A and what is B? Let's figure it out. So more side work. All right, kind of cross-multiplying should get me back to the original numerator. What was the original numerator? Oh yeah, 2x. Then choose your strategic x's. So B is 2/3. Choose your other strategic x. Negative 3a equals negative 4. So a equals 4/3. Okay. Go back and rewrite your integral. Let me do it down here where there's a lot of horizontal room. I'm going to do my previous result is equal to x squared minus x plus integral of a was 4/3, so let me put that outside. 4/3 integral of 1 over x plus 2. Again, I pulled out the 4/3 right from the beginning, like I did for the last example. Dx plus 2/3, pulling that b out right away, over integral of 1 over x minus 1 dx. Can skip u substitution, and then finally I get that as my answer. Yay, we did it. Great. And then that's it. So hopefully that helps. Let me know if you have questions. Goodbye, y'all. Good job.